Hey, AP Physics 1 students. Thanks for joining me again. So in this video, we're going to talk about one of the most conceptually tricky introductory topics, which is acceleration. This word is used in everyday life in a slightly different way, sometimes a radically different way from the way physicists use it, from the way we will use it in this class. So I want to talk with you about acceleration, what it means, how to numerically calculate what the acceleration of an object is, and things of this nature. First of all, to say an object is accelerating, what does that mean exactly? It means an object is speeding up. So the object is moving faster and faster moment to moment. That's the ordinary way in which most people use the term acceleration. But when physicists say an object is accelerating, it could mean the object is slowing down, that the object's speed is decreasing over time. Or it could mean that the object is changing direction. The object is moving in a different direction moment to moment. So in any situation where an object ends up moving faster than it started moving, the object must have been accelerating during the time interval. Or if an object ends up moving slower than it was originally moving, the object was also accelerating during that transition, during that time interval. Or if an object is moving one way and at the end of some time interval it's moving a different way, the object was accelerating in that situation as well. Now, there's a way to summarize this, which is the following. Speeding up, slowing down, or changing direction, that means the object velocity was changing over time. So if an object is accelerating, then its velocity is changing. The magnitude of the velocity might change. That would mean the speed changes. And or the direction of the velocity might change. That would also be considered an acceleration. All right, so let's just talk qualitatively for a moment. Qualitatively about a few examples in which an object is accelerating, and we can think about whether that object is accelerating in the same direction as it's moving, in the same direction as its velocity, or whether the object is accelerating in the opposite direction of its velocity, things like this. So here's a few examples. Suppose an object has an initial velocity of 5 meters per second to the right, and later on, it's got a final velocity of 10 meters per second to the right. So the object is moving to the right. It ends up moving to the right even faster. If that is what's happening, then I guarantee you the object is accelerating to the right. An acceleration to the right will cause an object which is already moving to the right to end up moving to the right even faster. Here's another situation, so separate situation. An object is moving to the left at, let's say, 6 meters per second to the left. That's the initial velocity. And the final velocity of the object is 18 meters per second to the left. So this object has an initial velocity to the left and a final velocity also to the left, but it's moving faster. Well, this object was accelerating to the left. These are the easiest situations to appreciate. If an object ends up moving faster in the same direction that it was originally moving, then the object was accelerating in that same direction. Okay, but there are other possibilities. For instance, maybe the object is moving with an initial velocity of 4 meters per second to the left, and it ends up moving with a final velocity of only 2 meters per second to the left. As you might anticipate, sorry, to the right, moving at 4 meters per second to the right, and it ends up moving at only 2 meters per second to the right. In this situation, the object was accelerating to the left. So the object was not accelerating in the same direction it was moving. It was accelerating in the opposite direction, and that caused the object to slow down. Or perhaps the object had an initial velocity of, let's say, 10 meters per second to the left, and a final velocity of 2 meters per second to the left. So it started moving to the left. It ended up moving to the left slower. This means the object was accelerating to the right. So can we make sense of this? Well, yes, the answer is yes. The way to view an acceleration right now is kind of like the wind blowing on the object, for instance. Now, an acceleration is not a force. It's not a push or a pull, like the wind blowing on an object exerts a force on the object. However, as we'll learn in the future, forces, pushes and pulls, cause accelerations that point in the same direction as those pushes and pulls, those forces. So loosely speaking, we can imagine that the direction in which an object is accelerating is the direction in which it's being pushed or pulled. So let's see if that makes sense. Object is moving to the right. It's accelerating to the right. So it's like being pushed to the right. And it's already moving to the right. It ends up with a final velocity that is to the right and bigger in magnitude, a bigger speed. On the other hand, if the object is initially moving to the left and it's accelerating to the left, it's being pushed to the left, it's going to end up moving with a final velocity to the left, which is, again, bigger in magnitude than the initial velocity. It's going to end up moving at a bigger speed. On the other hand, suppose the object has an initial velocity to the right, but it's accelerating to the left. It's like being pushed to the left. It's going to slow down. It's going to slow down, and in this case, it ends up moving slower than it was originally moving. And finally, the object is initially moving to the left, but look, it's accelerating to the right. That makes sense. It's going to end up moving slower than it was originally. Okay, so let's just talk about the sign. Acceleration has a numerical value to it. So let's talk about the sign of the acceleration. Unless stated otherwise, I'm always going to consider my x-axis to point to the right. So the positive direction is to the right, and the negative direction is to the left. So notice here, in this first example, the object's acceleration points to the right, so it's a positive numerical value. And it's true that the object sped up. It was moving at 5 meters per second, and now it's got a speed of 10 meters per second. So in that case, that positive acceleration caused the object to speed up. But it would be a terrible mistake to think that, well, positive accelerations means speeding up and negative accelerations means slowing down. That's not true, because look at the very next example. The object's moving at 6 meters per second to the left. It has a negative acceleration because it's accelerating to the left, and it ends up moving faster as a result of that negative acceleration. So in this second situation that I've circled in pink, the object is accelerating to the left. It has a negative acceleration, but it speeds up. It's now moving faster to the left at 18 meters per second relative to its initial slower velocity to the left of only 6 meters per second. So it's important that you do not associate positive accelerations with speeding up and negative accelerations with slowing down. why don't you take a moment, you can pause the video and try to figure out what about the acceleration and the velocity tell you whether the object will speed up or slow down as a result of that combination of acceleration and velocity values. Pause the video and see if you can figure out a rule that tells you when an object will speed up and when it will slow down. Okay, if you were able to do it, congratulations. And for those of you who were just here to enjoy the show, I will present the Rosetta Stone for this situation here. All right, so if an object is moving to the right, it's got a positive velocity. If it's accelerating to the right, it means it has a positive acceleration. That's this example here. The object initially had a positive velocity and a positive acceleration, and it ended up moving faster than it was originally moving. On the other hand, here the object has a negative velocity value, and a leftward, that means negative acceleration value, and the object speeds up. It ends up moving faster than it was originally moving. So what's important to appreciate here, where's my eraser? What's important to appreciate here is that when the velocity and acceleration are both positive, or when the velocity and acceleration are both negative, then the speed of the object goes up. The object speeds up. So moving to the right and accelerating to the right is like, well, you're moving to the right and the wind is pushing you to the right, you speed up, or moving to the left and the wind, the acceleration is pushing you to the left, you also speed up. On the other hand, there are two situations in which the speed drops. The first is illustrated here. The object is moving to the right with a positive velocity, but it's accelerating to the left. It has a negative acceleration, and the object ends up moving slower than it was originally moving. So the object slows down in that situation. Okay, so positive velocity and negative acceleration, the speed drops, the object slows down. And in the final situation that I've drawn, the velocity is negative, the object is initially moving to the left, but the acceleration is positive, the object is accelerating to the right, and the speed ends up dropping as a result. So moving to the right, but the wind is blowing to the left, you slow down, your speed drops. Moving to the left, but the wind is blowing to the right, you're accelerating to the right, you also slow down. Therefore, it is not the sign of the acceleration being positive or negative that tells you whether the object will speed up or not. It's the relative directions, the relative signs of acceleration and velocity that tell you whether a moment later or a little bit later, the object will be moving faster or slower. Velocity and acceleration point in the same direction, object speeds up. Velocity and acceleration point in opposite directions, the object slows down. And you'll note at no point have I used the term deceleration. In everyday life, people use the term deceleration to mean slow down, but I don't like this term because people associate deceleration for some reason with negative acceleration, but negative acceleration doesn't mean slowing down necessarily. So let's use the term acceleration to mean either speeding up or slowing down or changing direction. We'll get there in a minute. And we'll never use the term deceleration, decelerate. It's forbidden to use it. We'll avoid using it because it just adds confusion. All right. Now, I haven't talked about the object turning around, changing direction yet. So let me do that now. If an object has an initial velocity to the right, and it doesn't matter if the velocity is bigger or smaller, but if the final velocity is to the left, okay, so initial velocity to the right, final velocity to the left, I guarantee you the object was accelerating to the left. I don't even care if it's moving to the left faster or slower than it was originally moving to the right. The fact that the object turned around means the object must have been accelerating opposite the direction of its initial velocity. So if I'm moving to the right, the wind must be blowing to the left. I must be accelerating to the left if I end up turning around and moving to the left. Similarly, if I'm initially moving to the left, my initial velocity is to the left, and later on I end up moving to the right, that must have been caused by the wind blowing me to the right. So this object must have been accelerating to the right during this process. Always, it's helpful if you think about the object as like a person on roller skates or something. So the person has an initial velocity to the right on roller skates. There's a strong wind to the left. That is what would be needed for the person to turn around and end up moving to the left. If you think about it this way, it makes it even more concrete what this acceleration direction is all about. All right, so we've just qualitatively discussed how the relative directions of velocity and acceleration lead to the object speeding up or slowing down, or in the case that the object turns around during the process. Let me adjust the lights in the classroom. They're on a motion sensor. Okay, as I was saying, or if the object turns around during the process, I know that the acceleration points in the direction that the object ends up moving. Actually, there is something more to say here, because take a look at this example here for a moment. If the object is moving to the right, but accelerating to the left, it should slow down. On the other hand, when the object starts moving to the left, if it continues to accelerate to the left, it should speed up. So maybe I can illustrate for you this entire process in kind of finer steps. Here we go. So maybe the initial velocity is a big value to the right, and then a smaller value to the right, and then a smaller value to the right, and then a smaller value to the right. And then the object stops. The object must be at rest at some moment. Think about that. The object's moving to the right, slowing down, slowing down, slowing down. It must stop if it is then going to move back in the leftward direction. And then, after it stops, it will speed up to the left, move faster to the left, move faster to the left, move even faster to the left, and have some final velocity to the left. So the object initially had a velocity to the right, but finally had a velocity to the left. And there's actually three different things going on here. So the whole time the object is accelerating to the left. Because the object is accelerating to the left the whole time, whenever it's moving to the right, it's slowing down. So it's moving to the right until it comes to rest, and at every moment that it's doing so, it's slowing down. When the object ends up moving to the left, its speed is going to rise, because remember, it's accelerating to the left at every moment here. So it's accelerating to the left as its speed drops, and on the return trip, it's accelerating to the left as its speed rises. And it's even accelerating at this moment. When it's at rest and turning around, it is accelerating. If it were not accelerating at that moment, its velocity would not be changing. And if its velocity is not changing, it would just stay at rest at that position. But it is at that moment that the object is turning. It's changing direction. In the kinematics packet, I discussed the situation in the context of a ball that you throw up into the air. So the ball is always accelerating down when you toss it up. So what does this look like? The ball is accelerating down, but its velocity is up. Because velocity and acceleration are mismatched, the object slows down, and for a brief moment, for an instantaneous moment, it stops. But it's still accelerating down, so its velocity will not remain with the same value of 0. The downward acceleration makes it turn and start to move down. Now for the downward part of the trip, the velocity and the acceleration are in the same direction, and the object speeds up until it strikes the ground. So it is possible for an object to be at rest, meaning its velocity is 0, yet its acceleration is not 0. In such a situation, the object will not remain at rest. It will start to move a moment later. And if you think about it in terms of the acceleration being like the wind blowing, this also makes sense. If I have a piece of paper on my desk, there could be some moment where its velocity is 0. But then I open the window, the wind blows in, and at that first moment, the piece of paper is not moving, but the wind is pushing on it. That means the piece of paper has no velocity, but it is accelerating. And by virtue of accelerating, a moment later, it will have a non-zero velocity value in whatever direction the wind was blowing on it. Okay, let's get quantitative now. Let's get quantitative. So I'm just going to show you one example, and then you'll have the chance to work on some problems like this in the kinematics packet and the associated homework. All right, so here's the example. The example is the following. I'll write this as a word problem. So let's say a bird is flying west at 10 meters per second. 2 seconds later, the bird is flying east at, let's say, 15 meters per second. What is the bird's average acceleration during this time interval? All right, so just like velocity and speed, you can find the average speed over across a time interval, or the average velocity of an object during or across a time interval. Or you can talk about the speed and velocity at a moment in time, which would be the instantaneous speed or instantaneous velocity. You can also calculate the average acceleration, that is the average rate of change of the velocity of the object during a time interval, or you can talk about instantaneous acceleration. It's much easier if we just stick to average acceleration right now. So to start, let's draw a little picture here for ourselves. I will draw an x-axis. And the right is the positive direction based on how I've drawn my x-axis. So what's the situation? The bird is flying west at 10 meters per second. I'm going to say that the positive direction is east and the negative direction is west. So the bird is flying west at 2 meters per second. I don't know, 10 meters per second. I don't know where the bird is but I'm just going to draw it somewhere, and its initial velocity is 10 meters per second. The arrow tells me that it's 10 meters per second west. And 2 seconds later, it's flying at 15 meters per second east. I don't know where the bird is located, but its final velocity is 15 meters per second east. All right, now what is its average acceleration during this delta t equals 2 second time interval of transition? Let's calculate it. The average acceleration of the object, did I give you this definition yet? Not really. I think I should write this down first. So I'll write it here. The average acceleration of the object is the average rate at which the object's velocity changes. It's the average rate at which the object's velocity changes. So let's compute that. If I calculate the change in velocity and I divide by the change in time, the time interval, then I'll figure out how much the velocity changed, divide by how much time that took, and that will give me the average rate at which the velocity changed during that time interval. So this is the final velocity minus the initial velocity. The change in anything is the final value minus the initial value, divided by the change in time. All right, let's see. The final velocity is 15 meters per second to the east. That's positive. So the final velocity is 15 meters per second. Now I subtract the initial velocity. The initial velocity is 10 meters per second to the west, but the west is the negative direction. So I have to subtract the initial velocity, which means subtracting negative 10 meters per second. And then I divide by the 2 second time interval. Let's keep track of the units here very carefully. Final velocity is positive 15. I subtract the initial velocity, which is negative 10. And 15 minus negative 10 is positive 25 meters per second, which I then divide by 2 seconds. Okay, 25 divided by 2 is 12.5. Now take a look at the units. The units are meters per second per second. Meters per second per second. I can treat these units just like I would treat variables or numbers. So meters over seconds looks like this. The units are meters per second squared. Let me get the lights again. The units are meters per second squared. This sounds weird. What does that mean, a meter per second squared? Well, it's a meter per second of velocity change per second. So at what rate did this object's velocity change? It was moving to the left with a negative velocity. It ends up moving to the right with a positive velocity. Its velocity was changing via an addition of 12.5 meters per second of velocity per second. Meaning if every second that went by, and 2 seconds went by, you added positive 12.5 meters per second to the object's velocity, you would end up with the proper final velocity. Let's think about that. The initial velocity is negative 10 meters per second. So after 1 second, if I add 12.5 meters per second, I'll get positive 2.5 meters per second. After the next second, I add another 12.5 meters per second onto the velocity, and I go from positive 2.5 plus 12.5 gives me positive 15 meters per second. It's the final velocity. So 12.5 meters per second squared, it could mean speeding up by 12.5 meters per second. It could mean slowing down by 12.5 meters per second. But in this case, the object slows down, then turns around and speeds up to the right. So it's better to think about it as just the velocity is changing by way of, in this case, adding positive 12.5 meters per second onto the velocity every second. Acceleration, just like velocity, just like displacement, has a direction. Because the average acceleration is positive, I know that the direction is to the east. So the average acceleration is 12.5 meters per second squared, comma, east. That's the answer. 12.5 meters per second squared to the east. Does this make sense in light of our previous discussion? Well, let's see. The object moves to the west initially. It ends up moving to the east. And that means during this time interval, the object must have been accelerating to the east. In fact, it was accelerating to the east with a value of 12.5 meters per second squared of acceleration. So the wind blowing to the east slowed the object down, stopped it, and then sped it up. Okay, as I said in the beginning of the video, this is a conceptually tricky thing. The main problem people have is they confuse velocity and acceleration. So I'll just say this. Velocity you can see easily. For example, if something is, for example, this marker, if something is moving up, I know its velocity is up. If something is moving down, I know its velocity is down. If something is moving, let's see, I don't know if the video is reversed, but if something is moving to the right, the velocity is to the right. But acceleration, you don't see acceleration. Like you don't pick that up. You have to think about that. For instance, if something is moving up, but it's slowing down, then its velocity is up, it's moving up. But if it's slowing down, its acceleration must be in the other direction. Its acceleration must be down. So watch this. This marker is going to move up slower and slower. Now, if you get good at this, when you see that, you may be able to quickly process that, oh, it's accelerating down for that to happen. Here's another situation. The marker is moving up faster and faster. It was accelerating up. In both cases, the marker was moving up, and it's very easy to see, oh, its velocity points up. But in the beginning, you'll definitely have to take that moment to think, but is it speeding up or slowing down? And that, in conjunction with the direction of the velocity, tells me what the direction of the acceleration is. Okay, so I hope this video was helpful in aiding you to complete the conceptual acceleration homework problems and the acceleration homework problems. There's 2 homeworks associated with this video. Good luck. And the next time we convene, we'll talk about a different topic. Okay, have a good one, folks.